Alright, so let's see. So we have only one question from your chapter 2, yeah? So I waited like the whole week to collect your questions. So the only question that we have from chapter 2 is example problem 2.2-3, and we're solving the rectilinear problems, okay? So your question is, a car is driving. I'm going to just copy it because it's not going into this recording area. Okay, select area. So let's go and copy the whole thing out. So the question is, there is a car and that is driving along a straight road, and we're going with 60 miles per hour. Yeah, and your driver suddenly, yeah, this is very important, applies the brake. So when you suddenly apply the brake, your car is gonna decelerate, and it decelerated with a constant rate, 10 feet per second square. Yeah, so pay attention to every unit. Some students are not paying attention to the unit they're dealing with. See like how different that two units are. One is in meter per hour and the other one is in feet per second square. Yeah. So the first sentence we read it, and that's we notice is in meter. The second one we read it, the second sentence, and we noticed the unit is in feet. You know, don't go so fast when you read any of the physics or mathematics or dynamics, statics, all right, problem, because you gotta keep your brain very calm to be able to see what you're reading. I'm trying to teach you so many times to be able to recognize what you're looking at and what you are seeing. You know, a lot of the people, their mind is not with their eyes. So you have to make sure that your mind is with your eyes. So you recognize what you are looking at. And that is a difference between people who are very successful and people who are not. Okay, because they don't recognize what they're looking at. They don't recognize what they're saying. Okay, so make sure they don't recognize what they're listening. So recognition is very important in science, engineering, and mathematics. Okay, right. Anyway, and of course, field is a technology. Technology is totally a part of already in the all of them. Okay, science, mathematics, engineering, and technology goes into all of that. So anyway, so the driver suddenly applies the brakes, decelerate the car, but he didn't decelerate it whatever. He decelerated at a constant rate, 10 feet per second square. And we got all that information, and we write that down. The starting velocity in this problem, not of that car, not outside, where the problem starts. Okay, at that time your car is driving with 60 miles per hour. Where this situation described in this problem start, the car is at 60 miles per hour, and that is your starting velocity. Then what is the stopping distance of the car? We want to know, what's the stop distance? And the deceleration of the car, again, is going to describe, what the deceleration is, to remind you what that is if you don't remember it. So if the deceleration of the car is a function, okay, and if we want to see this deceleration, not a constant rate, but as a function of the distance traveled, and it will be given as acceleration is equal to minus this little thing is a square root, and then your distance, okay, feet per second square. So here you're given a relationship between the acceleration and the stopping distance. See, so that's a position. Position means where you stop, okay? So every time we think about a position, where's my drawing on the line thingy? One moment, let me get this, okay? I'm gonna go ahead and draw this for you. All right. Okay, so every time, okay, you stop, and don't forget this position line, yeah? You're measuring on a line with numbers, yeah? And we have different lines, by the way. We have velocity line, we have position line, and we have acceleration line. Okay, don't forget any of it. What am I drawing? This is crap. All right. So anyway, I want to write it like a acceleration here. Okay, but I can't do it. Fine, let's try it again. Anyways, this is acceleration line. Okay. This two is something that the object feel. This one is the objects actually take physical movement and change the position in the world. Okay, this two thing is happening on that object. Also, please recognize what's going on in the motion. Okay, so anyway, these are the different aspects of different character that arise when a body starts a motion. Okay, so anyway, so here is the acceleration and the position relationship is given to you, and that relationship is very special because this type of deceleration is measured as a function of the distance. Okay, so that's what it's meaning. A function meaning like we're looking at very small changes. That's what it meant. Okay, so we're looking at a very small changes. All right, very small. Again, very small. Now where your S is your position is in, again, feet. See like how it determines, hey, I want my answer in feet. Now we're dealing with two different units. One is a meter and the other one is a feet. But we gotta make it with feet for this question. Yeah. So what is the stopping distance of the car in this case? So everything is now in your head, okay, given to you. The starting velocity, which is very important here, meter per hour, yeah, and your meter per hour, and then your ending, we want it in feet, okay, ending distance, we want it in feet. Now, one of the students had a lot of issue with the velocity stop, this one is just automatically understood, even though we wrote it down, because we know that you applied the brake and it decelerates, and it said it so here, stop the distance of the car. When the distance stops, there is no velocity. Now that's automatically understood. Whether we write it here or not, it just, in my brain, when I see stop, I know that there's no, velocity at that point. At that point of stop, yeah. So anyway, so then we write down, of course, the constant rate. The car is going decelerating, so meaning your deceleration, which is your A, since it is decelerating, you're in a minus direction, yeah. Again, when you're accelerating, when your body is going, you have a velocity going that direction. You also have if the velocity changes, you also have a acceleration going that direction. When you stop, okay, when you stop it, that acceleration go, all right, the object will feel the acceleration pulling you to the back, okay, so going to the negative direction, okay. So try to get all of that into your head, and that's why we wrote it here. It's very important to see this little negative sign right there, and that's just telling you, hey, I am my object of interest, the car, and I stop it, and it is trying. In order for a motion to stop, something got to pull. There is a force that is pulling. Yeah. Every time there is a force that is pulling you back, we have this. Okay. This is your car. When we see mass, it means that the object of interest, that's car and the driver on it. And this guy, see this? Oh my gosh, I hate this thing. This acceleration, let's just my drawing is so bad. This acceleration got to be negative to create this, which is going to pull that to the opposite direction of the motion. Yeah. So if you're going that direction, this is going to pull to the back, and what we're seeing, this, okay, negative acceleration is what is happening on that body, okay, when you stop. Okay, so I want you to really get it. Don't say like this thing acceleration is pulling me. No, actually there is a distinct force, and that force is happening right at your body, which is your mass right there. Okay, mass means we see the mass as a body. So because of that force, your acceleration, this body just get, all right, subjected to is pulling you to the opposite direction of your motion. Okay, so everything got to be in your head, that way. All right, and that's where this thing came from. Yeah, and of course it doesn't stop. It just want you to analyze. Okay, this is too easy, and this is very unrealistic in the world, even though it's so easy on the paper. But the real world is very much like this. Okay, so we have actually this type of deceleration. Okay, I shouldn't say velocity. This type of deceleration. Why? Because your car, right, acceleration is happening as a function of your distance traveled. Yeah, so we will look into the small changes of that two variable acceleration and the position, and that's where this comes from. Yeah, so what if your acceleration is not constant but as a function of distance traveled? At that time, what is this stopping distance is going to be? Yeah, so that's the question is about. So if you gauge the time, it takes about 5 minutes, to absolutely understand what is going on. If you don't understand, it is very difficult to calculate. Yeah, so make sure you spend about 5 minutes. Maybe for you it might be longer or shorter. I don't know. Depends on your brain. Yeah. Spend the time to actually understand what you're doing before you even start to calculate. And once you understand everything, let's get in. Yeah. Let me put this down and get this to going down. Yeah. All right. So now we're gonna start calculating it. So first we give this. Where's my thing again? Right. All right, so first we give this, okay, initial velocity, 60 miles per hour. We notice the unit, the final velocity completely zero because you decelerate and stop. And we gotta do one step before we get into the problem, and that is because your final answer want, okay, the distance traveled as in feet, okay? The problem set it. So therefore we gotta transfer this meter into feet. All right, so meters per hour, or no, this is not meter, sorry, miles per hour. What am I saying? So okay, 1 miles per hour got to be in feet. Okay, sorry about this. I gotta go back up. I made a mistake. This is not meter. This is miles per hour. Okay, be careful. Yes, miles per hour is even better. Yeah, all we have to do is change that miles and then hour into feet and second. And so we go down, and first we're gonna transfer this transfer the unit from miles per hour into feet per second. Okay, so when we do that, our, look at this, conversion factor is every 1 mile per hour we have 1.467 feet per second. Okay, so now I have 60 of them, so that was 60 times 1.467. Yeah, and we convert it and we get 88. Yeah, 88 something, 0.02 feet per second. So this is what we get, and we will be using the initial velocity in feet per second. Yeah, all right. Then the very first one is we have to calculate the stop distance with constant deceleration. Here is your deceleration, your little minus sign, and then we have our magnitude, which is 10, our unit feet per second squared. So we're okay, yeah, everything. And we're gonna use this kinematic equation. We have a lot of them, yeah, 4 of them. For constant deceleration, we have 2 different things going on. We have constant, okay, C-O-N-T, C-O-N-S-T, I say, constant acceleration equation, yeah, 4 of them. And then we have non-constant, which is, I call it calculus, yeah. Some people call it derivative and integration, yeah. So that's up to you. D for derivative and integration for this wiggly thingy, yeah. And we also have a function of time, okay, equations in there with calculus. So with constant deceleration, we're going to choose one of them, and we will of course choose something that has distance travel, which is your little s, yeah, and velocity and acceleration, because these are everything that is given to you, yeah. So we can be able to find this by plugging in all the values into these variables, given variables. This is given, that is given, this is given to you, so therefore we can find this, yeah. So that's your algebra. All right. Okay, now we're gonna substitute everything we've got, yeah. Substitute everything we have already. That's our transferred, converted value, yeah, from miles per hour to feet per second square. We put that in, yeah, and then of course your deceleration, yes, and then this is from your equation. You calculate it, and you're gonna get distance traveled, and we get about 387.38 feet. Okay. I don't know what your video here is gonna. I don't really look at it, but she should get it approximately the same. Okay, let me turn this thing off. Approximately the same for that. Okay. So, anyways, let's go one little back. I just want to check what they get for the end. Okay. They gotta get something in there. I don't have time to look at it, but they will get about the same as that. Yes. It's so hard to find this thing. Gosh. Yeah. See, well, we're on the same page. Yeah. All right. I'm gonna go back into here. Anyways, this is with a constant. Yeah, constant deceleration. Then the second one is do it, with the function of distance traveled. So we will get into the calculus, calculus, and your question is very nice because it gives you the relationship between the acceleration, variable deceleration in this case, and the position, which is your distance travels, where the car stops, is given to you. That is minus square root of s feet per second square. So that's even better. So we're going to start with what it gives you. Maybe I calculate a little bit different from her calculation in there, yeah. And then we're going to use the equation, yeah. And this equation is from your handout, if you remember it, okay. Your acceleration, yes, is the velocity, and times the little small changes in velocity over small changes in the distance, yeah. So if you forget about this, all right, this comes from a very easy, okay, equation that we started, the change, remember the change in position by time, and then we go acceleration is the change in velocity, per time, and then of course this is just a regular change, so we replace that with the little change d. So all the triangles are replaced by d, and then we get rid of the time, and from there we get this, okay. So when you put that in, okay, you're gonna get velocity dv by ds equal to a. So make sure you go back to my chapter 2, yes, to replace this 2 in there, and then do your algebra, and you will end up getting this. Okay, all you have to do is just replace with d. Okay, So like that. I'm doing this again for you. I shouldn't, but in your mind you should see it. Yeah, some student cannot be able to see it, not yet, but eventually you will see it. Yeah, you will see it with your mind. Anyway, this is D. Yeah, and then of course we will replace in this. Okay, meaning like I am putting like this. Yeah, go this way. That's your college algebra. Yeah, and this is the same for this example right now, because you're analyzing your motion in that time interval. Automatically we understood. Okay, and we put this in there. Yeah, so if you put that in there, you get this. Yeah, I shouldn't be doing this for you again. Now I'm doing that again for you. Yeah, so like that. Of course your A is now going up. Yeah, because you put it into here. You put this thing in here. Yeah, and then of course you put this to that side. Yeah, because we want to go that way. So I am going to write this here. Yes, and you will get of course. Yeah, on this side is ds. Yeah, and then your A is like this. Yeah, so all I did is I put this on that side. Yes, and then of course you're gonna put this to that side, and when you do that you get this. Okay, yes, so v dv by ds equal to A. Yes, it comes from there, very simple one. And some student can't link from here to here, and they need to write that down. So make sure you do that in your head. If you write it down about 5 times, you got it, and you don't have to write it down anymore. Yeah, you can be able to just see it very easily. Of course, and once we finish it, we're gonna put this, yeah, to the other side. Yeah, see, look, yeah, go there, and we're gonna put this with this. Yeah, because it's given there for you. See, so v dv equal to minus square root of s and then ds. Of course, many people calculate in many different ways, but these are what is happening in your head. By the way, I wrote it so that way you can get it. And then of course I said every time you want to get rid of this little d, okay, you can integrate. Yes, if you want to get rid of that, you can integrate it. So I start integrating it. Yeah, when I get, so in order for me to get rid of this little d, change, okay, and just try to get the value at that moment, I do integration. So that's just an operation, yeah, operation of the in mathematics, trying to describe that, hey, I am just looking at by ditching all of the directions and everything, and I'm looking at that moment. So when you do the operation, first you have v. Okay, now I am going to teach you the calculus. So how do we get rid of the little change by integrating it? So your integration is happening, motion analysis that is happening from, okay, 0, okay, your initial and then your final. So 0, I'm just going to write on 88, and then this is 0, okay, your 0 and 88, my brain is like backwards of your brain. I usually go this way, but anyways, it's the 88, and then you're going to come to a stop like this. Okay, so that is your the very first given data, 60 miles per hour. So your velocity, yeah, your velocity initial, and then your velocity, okay, final. So one of the students I were talking, I said, this is your final, and this is your initial, right? So you want to put that in. Anyway, so put that in here, 88, and then 0. So now you get the idea of what's going on, and you're analyzing the object, which is your current U on it, yeah? And so if you just want to look at the value, we gotta get rid of the change, yeah? So we're getting rid of whatever the change happened between these 2 points. Again, the points are very important, see? So that's how we're linking to the graph, yeah? Graphical representation of the motion analysis. So anyways, start 88 and then ends over there as 0, yeah? Because we're looking for the stopped distance on that line. So anyway, when you get there, we have to do integration, and that integration is happening from here to here. Yeah, so we're getting rid of the change and just want to get what's going on in pure value. So when we do that, number one, you're gonna put all the hidden power. So when you look at V always has a hidden power of 1, yeah, up there. So I'm just gonna write the 1 right there. So V to the power 1, yeah. So that's this little V, and I want to get rid of this derivative, which is the little change of V. So therefore, I'm gonna put that back into that change. So this means like we're differentiating, meaning, hey, I have this, and my change is this much. Now I'm putting that change back again into it. Where did I come from? Yeah. So that change to get rid to put it back in mathematically. First we're gonna look at the power. Second, okay, we're gonna put the power back in. We're gonna add 1 to the power. Yeah. Every time you add 1, you've got to adjust what you added. Okay, mathematically by multiplying that variable with the adjustment factor, which is this guy. Yeah. So all you have to do is now your power is, we put 1 back in, so you get 2. Yeah. So we're gonna divide that by 2. Okay. So now your resultant that you got is 1 by 2 V to the power square. Yeah. So it means that instead of differentiating, separating the change, and we look at regular one and the change that happened, we integrate it by get rid of that change. So if you integrate it, your change is erased. When the change is erased, that change is put back into where it came from. Okay, so this is the original one. So therefore, every time you wanna put the change mathematically back into where it came from, remember we go forward in the motion aspect, and we go backwards. Yeah, backwards we do integration. Forward we separate the change, so we can be able to study the little amount of change, what's going on. Yeah. Now we can put that little amount back in if you want to go back to the original thing. That's what we're doing, and represented by mathematical expression like that. And we play with the number, meaning we are looking for the magnitude. Okay, magnitude meaning like the value, right? The amount of that velocity is this much. Yeah. Hidden power, reveal it. We got 1. Add 1. Okay, every step of the integration we add the power 1. Resultant 2. You're gonna use that 2 as a denominator, and then create the adjustment factor to multiply with the given variable. Yeah, and then write it all down. So 1 by 2 V to the power 2 is going to be your result of integration operation for that variable V, okay, with the change dV. And that change is, again, this is nothing. This is just showing you this happened in between 88 to 0. Okay, yeah. Then on this side, we do the same thing. We integrate to get rid of this little change, all right, ds. And we gotta fix this, all right, minus square root of s back to it was before. Yeah. So we do the same thing. How do you do the same thing? Your s is that, yeah. Your power reveal. Your power is 1 by 2. You're gonna add that. Yeah. So if you add it, you're gonna get this. Oh, wait a minute. Let me go down the page. Okay. This is on this side, so we are still on the left side for this page. So anyways, let me just I'll do that again on the other page. Okay. So anyway, so this is for the left side, which is this guy. Yeah? And of course you put the value into here. Yeah. So the very first one is 0. So you're gonna go 1 by 2. 0. Okay, the second one is, so if you want to know how we write that, I can write this for you. I am going to the right side already. I should, okay, one moment. Yeah, let me get rid of this to get some space. So this is very easy. It just, yeah, putting the 0, yeah, to the v square, yeah, and then the other one is of course 88, yeah, putting 88 square. It said it so, yeah, go from 88 and 0. When you write it down, the final, every change is final minus initial, yes. So initial is 0. 0 is hard to write it. So anyway, so that's what you're doing. So final minus initial is going to give you the change. Here, of course, a little change. Yeah. So anyway, so that is what you're seeing. Okay. So 1 by 2. So 1 by 2 times 0 is just 0. So you're going to end up getting minus 1 by 2, 88 squared. Yeah. So this, when you calculate it, you will get a value. Now we will move down to the second one. Yeah. The right side, I was already on the right side. So anyway, so when you calculate it, you're going to get minus 3872. Okay. All right. Then leave the left side, and then we go to the right side. Right side, we do the same thing. We call the integration because we want to get rid of this thing. Okay. So in order for us to do that, we do the same thing. First, your power is like this. Okay. So therefore, square root has a power of 1 by 2. Yeah. Reveal the power, and then we're going to add 1. Yeah. So when you do that, your power become 1 by 2. Yes. 1 is 2 by 2. Go 2 by 2. Yes. Because we want the same denominator. Without the same denominator, you can add it. So now we can add it. So your total is 3 by 2. Yeah. So once we get this, we can be able to make the adjustment factor, which is just flip it, right? So now we get the adjustment factor like that. And that's what you're seeing here. Yeah. So minus 2 by 3 s, and then 3 by 2. Now the ds is gone. So now we have starting point, ending point, 0s. And this is what we're trying to find. Yeah. So then we put it into s. 0 is automatically understood. So every time we see 0, we don't even write that anymore. Yeah. We just go straight in. Yeah. So we just go this. So minus 2 by 3 s, 3 by 2 is on this side. And the left side we already calculated, minus 3872 equal to minus 2 by 3 s, 3 by 2. Okay. Use that in the Excel to calculate it, or you can put it in a calculator if you want to. Yeah. But I usually use Excel to calculate that, or I use MATLAB to calculate. I program the whole thing to calculate it. I don't even write this anymore, it's just too long. Yeah. This is just writing that for you so you can see, because some students still doing it by hand. Yeah. So anyway, so 3872, and then 2 by 3 s, 3 by 2, yeah, your power. That's because we cancel this minus. Yeah. See, canceling the negative sign. And we're going to move again to that side. So when you move it, 3 by 2, flip it. Then calculate that, you get 5808. We have a square root and then power 3. So we can transfer that to the other side. In order for you to get rid of this, you got to do this. Yeah? You can multiply with that on both sides. So this will cancel, and you will get 1. Since you multiply with this, you also have to multiply with that on this side. Yeah, 2 by 3. Calculate it, and you will end up getting about 323 feet. All right. Just put it in the Excel, and it will give you 5808 to the power 2 by 3. How much is it? Enter. Yeah, and it will give you 323 feet. Again, your variable deceleration. That's why we use a calculus. Okay, your integration and derivative. Why? Because our acceleration is variable. Because this variable meaning it depends on whatever this s is. Yeah. So that's what it say. So that whatever the S is, we calculated, and that's a 323 feet. Constant is about you're getting 38 something. Let's go back. What did we get for a constant? Constant, we got a 387. Yeah. So 387. So with constant 387 feet. With variable, you only get 323. Yeah. So constant is too perfect. It can't happen most of the time. This is more realistic start point. So for application in the real world, yeah, you can calculate in car accident, yeah, so and so incident, and you're gonna give a range, including both types of deceleration, yeah. So your range could go like plus or minus, yeah, 5% error or 2% error. So you could give it like between 320 to 390, yeah. So that is a pretty good range. So 320 to 390 is your stop range. Yeah. Never ever give the exact one. You will go into serious trouble in real life. You always cushion with the error. Yeah. You can go reasonable error is about 5%. If your error is 20%, it's very inaccurate. The 5% has a very good and reasonable prediction or accuracy. So anyways, the variable means we are here analyzing the small change, which is your differentiation. And that's where your calculus, integration, and differentiation come in. So every time we have a small change, variable, we look the function of something, and to get rid of this, we operate that. Because your motion is already going, okay, from position to getting the acceleration and velocity. When we say acceleration, okay, don't forget the gravity word that we use back and forth between acceleration due to gravity and gravity force itself, and it confuses you. It's because every time we talk about acceleration, it is a common sense and automatically understood that your mass is being subjected with a force. Without that, you won't get this on it. Okay, so make sure that you get it. So when you're studying the motion theorem, okay, in order for you to go back to what is this and what is that, you got to get rid of the change that just happened in that interval, time interval. So you got to go backwards in that time interval to be able to analyze, hey, what is this and what is that? Yeah, and you have two things going on. One is a constant, and the other one is a variable, which is instantaneous. Yeah, instantaneous and variable. So anyway, so that's a problem, and I just finished it. Yeah. Now I'm going to bring you back to our engineering world or engineering technology world. Yes, this is no good. I'm just going to ignore it. That's just automatic grammar. We don't need grammar in mathematics. So anyway, so this is I'll give you another code to calculate. Of course, we program everything we need. Yeah, see, I already put the conversion factor, the stop, the starting point. Yes, because starting point is in miles per hour, I gotta convert to feet per second because your problem wanted in feet for your stop distance. Yeah. And then I program everything into this one. Shouldn't be a constant. You can also write it with a symbol. Yeah, you can make it like little b or c or whatever you want to call it. And then I'll go down. Yes, we put in the constant acceleration. Of course, I want an s, so I already did the mathematics and take the s out. Yeah, and already calculate this in this way. Okay, not I don't write it that way because you have to take the s out of it. So you wrote, so that's the only time, yeah, you gotta calculate, and once you program this, you don't have to calculate like above that we just did anymore because you already programmed it. So whatever problem it comes, many different variation of the same problem, all you have to do is change this, yeah, change the value of it, and it will automatically calculate that for you, because we want to print the results, and we coded, please give me stopping distance for constant deceleration in this way. And then another one is we come into the acceleration and square root, yeah, which is your variable deceleration. And we program that again and try to get the distance trouble, which is your stop distance in this way, yeah. Then again, call the result to be printed like this, yeah. And when you run it in the MATLAB like this, yeah, so you script it, and here the same code, I just copy and paste it right in there, yeah, and then you run, and it will give you the answer, yeah, and the answer I copy and paste it back here for you, yeah. So you get the constant deceleration, you get 387.38, and then stopping deceleration distance is 323.21 feet, okay. So your range is plus or minus 5% error before and then 5% error after, so you have very safe covering constant and variable deceleration for stop distance, yeah. So anyway, so that is the answer for the question from the class 4 chapter 2.